Hello, first video of the school year, and what I'm going to look at is why centripetal acceleration is v squared over r. Okay, so I've drawn this rather beautiful circle, and I want you to imagine I've got an object that's going around the circle in this direction. Okay, this is the centre of the circle. I'm going to call it 0. I'm going to think about the particle when it's at this part of the circle, which I'll call A, and it's going to this part of the circle, which I'll call B. Okay, so we've got it coming this way around the circle. It's going to go to A first, then it's going to go to B. Now, we know because it's going around a circle at a constant speed that its velocity is going to be changing, so it must be accelerating. And we know, because you listened to everything that you were taught last year, that acceleration is equal to the change in velocity divided by the change in time. Now, what's the velocity at A? Well, we know that it will be going in this direction at a tangent to the circle. Let's call it V1. We know B, it's going to have changed direction. So these two velocities, these two arrows should be exactly the same size, but we've got a change in direction. And because we've got a change in direction, that means that we've got a change in velocity. Well, if I want to know what the change in velocity is, all I have to do is I can look at the change in velocity is equal to the final velocity, which I've called V2, take away the initial velocity, which I've called V1. So if I want to know what the change in velocity, I've simply got to do V2 take away V1. Now, we know they're the same size, but the change in velocity isn't 0. The reason it's not 0 is because I'd have to draw a vector diagram. So V2 I've got going in this direction here. That's this vector. I've tried to draw it. I don't think I've got the angles quite right. So this is V2. Then if I've got to take away V1, well, minus V1 would be going in the opposite direction to V1. So I'd have minus V1 going in that direction. And that would give me my resultant vector. And my resultant vector would be, I'm just looking for a new pen to use, there we are, would be, well, it's not really a resultant, is it? Because I suppose I'm adding V2 plus negative V1. That there is going to be my change in velocity. Now, let's just have a look at some other things with this circle. Let me draw the line in from there to there. And I'm going to call this angle here theta. Okay, so I've got the angle that it's changed by is theta. Now, V1 is perpendicular to this line, V2 perpendicular to this line. So can you see that the angle that I've got between V1 and V2 would also be theta? Okay, that's going to be important in just a moment. Now, what I also need to know is I need to think about this distance from A to B. Okay, now this is where you just have to, it doesn't really get tricky, you just have to think that this will only work for very small angles of theta. If I know that it's going at a velocity of v and it's going along this arc here, then I could work out the distance between A and B, because I could go, well, the distance it's going to go, or the displacement, I suppose, is equal to the velocity multiplied by the time. Now, the velocity is v and the time is t. Okay, so I've got that the displacement from A to B would be v times t. Now, it won't quite be, will it? Because we've got this as a curve, so that would actually be the distance that it would go. But if theta was very small, then it would be the same distance and displacement. So this is working when theta is a very small angle. Now, we've got two different triangles here. Both of them are isosceles triangles. The length of this side is r, the radius, and the same for this side. For this triangle, we've got a length V1 and V2, well, they are the same magnitude, and the angle in between them is theta. So they are similar triangles. As I'm sure you could all tell me, similar triangles, what we can do with those is we can look at the ratios between the sides, because the ratios between the sides must stay the same. So if I was looking at the ratio between R and V, I could say, I might want to say V, or V1 or V2, but both of them have got a magnitude V, divided by R. So V divided by R must equal to change in velocity, because that's this side of the triangle, divided by, well, this would be A to B, which we've said is V times T. Okay, so using similar triangles, we get this. Now, at the start, we said, well, acceleration is change in velocity over time. Look at this, we've got a change in velocity and we've got a time. All we've got to do is multiply up that velocity. So, can you see that becomes change in velocity over change in time is equal to V squared over R. Now, luckily for you, you won't need to be able to derive this in the exam. But I know you guys wouldn't be happy unless I could show you vaguely where it was from. So you need to be able to use this equation. You need to know the direction in which the acceleration's acting in. I wonder whether you can think what that would be, especially sort of thinking, looking at my diagram here, it sort of works. And you need to be able to use it for lots and lots of calculations. Hope you've enjoyed this video, hopefully the first of many to come.